Okay, let's get started. Thank you very much for coming. Today, we're very happy to have Dr. Steve Miller here from CSU. Steve received his bachelor degree from UC San Diego and a PhD in atmosphere science from Colorado State University. After that, he went to NRL at Monterey for 7 years, joining the satellite meteorological application section there. And then he came back to CSU in 2007, joined CIRA as a research scientist and also a deputy director. His areas of interest include satellite-based remote sensing of the Earth and atmosphere system. His mineral dust detection algorithm for MODIS and CWIFs were among the first to exploit the blue band absorption properties. And in 2005, Steve published the first satellite detection of a widespread bioluminescence phenomena, the Milky Sea. I think we'll see that maybe in the screensaver or background of this computer screen. And using the DSMP operational line scan system. And he's going to talk about the day-night band Suomi NPP today. Steve?
Thanks, Emily. Okay, well, good afternoon, and thanks for coming to this seminar. Again, my name's Steve Miller. I work up at CSU. That was a great introduction, printed off of maybe something that was 5 years old, but still mostly accurate. Um, Hopefully, I'll update that at some point. But what I wanted to tell you guys about today was something that's really updated and really new and exciting, I think, and that's the capabilities of this low light sensor called the day-night band. And it flies on the Suomi National Polar Orbiting Partnership satellite. Excuse me. So I have a lot of slides, and hopefully I tend to talk fast, but I do have a lot of pictures in here, so I can probably keep this on time. The outline is first I will introduce VIIRS. That's the sensor on which the day-night band is part of and its capabilities, and then focus in on the day-night band itself, and then give you a lot of different perspectives on what it can do, namely detecting light at night, be that artificial lights, moonlight, or other natural sources of light emission at night. And then maybe look a bit to what we can expect or hope for in the future, and then conclude. So we have a nice picture of an aurora here, one of the many things the day-night band can see. But first, maybe a brief history. Our field of satellite meteorology isn't too old, maybe half century or so. So we can go back to the 1960s and say that's sort of the beginning, with the TIROS satellites in the 60s and the Nimbus high-resolution radiometers, slowly getting more higher spatial resolution, more channels over time, TIROS operational system, TOS. Then it kind of graduated into the first of the series of very high resolution radiometers. We started to get wider swaths and more detail, more radiometric accuracy. The operational line scan system on the Defense Meteorological Satellite Program was declassified. It was actually back in the 60s when it started, but it was declassified in 72. And it was sort of really the first low light visible sensor. And we'll talk about some of those capabilities and what's been improved upon since the OLS. Then many people know about the advanced very high resolution radiometer, the AVHRR. That's been flown by NOAA as its operational polar satellite for many years. And then in the late 90s, early 2000s, we saw a couple satellites from NASA come out, the Terra and Aqua satellites carrying the MODIS sensor, and that really took a big leap forward in terms of capabilities. Now we're looking at the next generation NOAA sensor going from AVHRR to what's next, and that's the Joint Polar Satellite System, and VIIRS, which I'll talk about next here, the Visible Infrared Imaging Radiometer Suite. It's one of 5 sensors on the Suomi National Polar Orbiting Partnership satellite. So it's a sun-synchronous satellite. It was launched back in 2011. And it's the first of a series of this Joint Polar Satellite System constellation that'll be going up, the first installment in 2017. And it tries to combine the best of all worlds of the previous sensors, legacy sensors, MODIS, AVHRR, and OLS. Many of you might have heard of the debacle that was NPOS, and that program kind of failed and it was canceled, and NPP came out of that. And this is probably one of the few good stories that came out of that whole thing, was that we had a day-night band that was a requirement from the defense part of the NPOS tri-agency agreement. They wanted low light sensing at night, and so it was on there. So even after NPOS went away, the day-night band stayed, and it's part of the next generation JPSS. So what's on VIIRS? Well, 22 spectral bands, narrow bands in the optical part of the spectrum from about 0.4 to 12 micron. There's the legacy bands from AVHRR are shown here highlighted. So 6 bands versus 22. We've gone to factor 3 or 4 higher spectral resolution. Spatial resolution, AVHRR 1 kilometer, and we get down to 750 and 375 meters for VIIRS. But the sensor that is really new and novel, unique, is the day-night band. It's a low-light sensor that we'll talk about, and that's the focus of this talk. But in terms of VIIRS and its improvements over Heritage, well, Swath has a wider swath than the previous sensors, 3,000 kilometers wide. And at the edge of scan, the pixel resolution is much better because it actually decreases its pixel size as it goes out to edge of scan by changing its detector field of view. So it preserves sort of a near constant pixel size out towards edge of scan, as opposed to these growing pixel sizes that we got on the previous sensors. So when you look at scan edge here, you see much more detail in VIIRS than even MODIS. And then there's no gaps near the equator as these swaths go across, so they're so wide they overlap each other. There's many applications ranging from the land surface, ocean surface, aerosols and radiation, and imagery from VIIRS. Examples of that shown here, a true color image over Texas, where we're doing some multi-spectral techniques to detect lofted dust. We can bring it out in various colors once we detect it, and that's by virtue of all the spectral bands we have at our disposal. Same thing that we can do with snow cover. This is a scene over the Great Lakes. Obviously, there's snow and cloud and actually some lake ice as well. With the multispectral information, you can turn this into something like this, where in this case the low clouds have been colored, cirrus clouds have been put into magenta, and the snow has been left in white. And these are just games that you can play once you have enough spectral information to decouple the various elements of the scene by their spectral fingerprints, if you will. So that's what we're able to do these things in the daytime. These are 2 nice daytime examples. Unfortunately, a lot of these nice techniques go away at night because we don't have those visible bands in the solar reflection to discriminate between clouds and different clouds, phases, and snow and dust and those kinds of features. So the focus of this talk is really on the new piece of VIIRS, the thing that's really different from all the previous sensors up to this point. An ability to see visible light at night from many different sources. So there's many motivations for this, but primarily, our ability to describe the nighttime environment is really limited at night from thermal emissive bands. These bands of wavelengths maybe 3.7 micron or longer. To detect things in general and characterize them, you need to have some kind of contrast, be that spatial contrast against the background, a spectral contrast, a changing signature, if you will, when you look at 2 different bands, or temporal changes, where something is changing and the background is not. With a polar orbiter, you're kind of limited really in terms of your temporal resolution. You get maybe 1 or 2 good shots per night, unless you're at high latitudes. So you're really playing around with spatial and spectral contrast. These things are very limited at night from thermal bands. Things like low cloud and fog, they blend in a lot of times with the thermal background. Optically thin aerosol just can't be seen, especially fine mode things like smoke and pollution. Surface properties, like we were looking at the snow cover, that just turns into a uniform scene. You can't see the snow at night because it's thermally looks the same as the surrounding background. And then there's also problems even when you can use spectral signatures for looking at low clouds. If there's thin cirrus in the way, it blocks that. The cirrus actually is very opaque in the thermal infrared, so it blocks anything below it. So also quantitative descriptions at night are difficult to do. We're limited to radiometric brightness temperatures. For clouds, for example, once you get to a certain liquid water content in the cloud, or liquid water path rather, amount of cloud water, the brightness temperature won't change anymore. It's just kind of flat. So clouds optical depths 10 or greater, you just can't say anything about. So that's a big limitation in terms of our cloud climatologies at night. We've sort of lived with this through the whole satellite era. What's been available is what we use, and we're sort of just kind of accepting of being in the dark for certain kinds of parameters, and we just wait till the daytime to look at them. But the message of this talk is that we're never really truly in the dark. There's all kinds of light sources at night that we can take advantage of if you have the sensor with the enough sensitivity to see that light. So in this cartoon, it was actually put together by Comet. And if you're interested in learning about this more, there's actually a link, and I'll make this talk available to you guys. When the moon is up, it's almost like a surrogate for the sun. It's reflecting off of clouds, off of the surface, smoke if it's thick enough, volcanic ash. If you don't have the moon, there's actually a number of other things that emit from the surface and the atmosphere as well. And I'll go into several of the examples of this in the coming slides. But first, to just kind of compare what we have now versus what we had before, the OLS, again, that's the Operational Line Scan System, the defense satellite that was declassified in 1972. It's been flying forever, but this VIIRS day-night band, well, of course, it has 22 bands, as we mentioned. OLS only had two, a VIS and an IR band. Radiometrically, the OLS had only 6-bit pixel depth, so 64 shades or radiometric resolution, and it was uncalibrated as well. The day-night band has 14-bit, that's 16,000 shades, and it is calibrated. Spatially, you see the OLS 5-kilometer pixels on the right here over Kuwait City, and if we look at the day-night band, you really have a paradigm shift in terms of what you can see. These are 0.74 kilometer pixels all the way across the swath. So it's kind of a revolution of resolution on all three areas of spectral, spatial, and radiometric. So what are some of the things that the day-night band can do? So we'll start with anthropogenic lighting. This is a global nighttime lights of the world map put together by NASA using Chris Elvidge's global nighttime stable lights data from the day-night band. And you can see obviously where your favorite city is or not. Over the oceans, not many lights. But where we do have cities, there's already doing some nice studies looking at light pollution, using the day-night band as a way of constraining how much light is coming from a city, and you can model that and compare it to actual observations. That's what's being done by the National Park Service, where they've looked over Las Vegas here, and they've used the day-night band as a way of seeing if their model was creating the right amount of light or not. And so once they compare their observations from an actual measurement on the surface, looking over the Las Vegas area, you see this dome of light at night. So a lot of light pollution, of course, from the Vegas Strip. They modeled that, and then once they said, okay, we've got it pseudo right, they could play games in the modeling world and change, for example, the shielding on the lights to see what this same dome of light would look like if they had best practices. They used the best shielding of the light, so not as much light was going up into the sky, for example. So you go from this current practices to best practices, and they can do these kind of simulations and show what the improvement would be. Of course, light pollution is important for a lot of things. Certain nocturnal species, their behavior, bats also are affected by nocturnal lighting, and even human sleep patterns as well. So the day-night band is being used for that. Also, when city lights go out, we can see them with the day-night band. We can compare previous nights where the lights were on to current nights when the lights might have gone out from a storm, in this case, Superstorm Sandy, and all the power outages along the Jersey coast there in New York City. This was right after the storm, and so I've colored this before and after difference in a way that the red areas are the areas where there's no longer lights where there were before. The gold areas are just stable lights, and greens are just new lights, in this case from moonlight reflecting off of clouds in the current image. but really red is what you're looking at here. And you can see over the next few nights, some of those reds go away. I'll go back and forward again, and you see some light recovery. So over the course of about a little over a week's time, a lot of the lights have recovered. If we zoom in here over the New York City area, this was actually an aerial photo looking toward the island there, and you can actually see One World Trade Center at the very tip there, still lit up even in the day-night band. So the 742 meter pixel resolution is great for resolving this kind of detail. And then you can see really bright up here at Times Square, matched up here in the photo. We can also see new lights that might correspond to, in this case, an aircraft disaster. The Air Algeria flight that crashed in Mali a couple years ago. Mali doesn't have a lot of natural lights or city lights around. I should say just a few cities here. So when you see a new light in this area, it really stands out. So this was before the aircraft crashed, and then actually when Air Algeria crashed, it created a fireball on the surface, and we were able to see that because the satellite came across within minutes of the crash. Just so happened, and this is the area. So you can see those new lights there showing up in that area. In fact, this is the thunderstorm that the aircraft flew through coming up from the south when it ran into trouble and it eventually crashed. So in these areas here are actually lightning flashes in the storm. And this was a confirmation of the location of that light corresponding to where the reported debris field was. So changes to the distribution of stable lights can be used either to look for power outages or for, in this case, monitoring disasters, search and rescue support. We can also look at anthropogenic lights in terms of ship lighting. These are ship tracks, well-known process by which effluents from ships will modify the microphysics of clouds, and you can see those ship tracks in the moonlight reflection in this case. We'll talk about moonlight more in a few slides. But at the tip of some of these tracks, for the first time now we can see with the day-night band, if you can see it on the projector, it looks pretty good. You can see these lights from the ships themselves. This is something you couldn't see with the previous low light sensor on DMSP, just the resolution is too coarse. Sometimes these lights take on interesting patterns in the water. These are squid boats. They use these really high mission xenon lamps to attract squid to the surface so they can catch them with hook arrays. But sometimes there's interesting configurations you see in the water. So this is out over the Yellow Sea, and it almost looks like a linear pattern in the water. These are all individual squid boat lights. This is what they look like from the surface, but they all seem to be lined up along this border. And it turns out that that border is politically drawn. These ships have GPSs on them. And in this case, we have the border lining up with a demarcation between private waters and shared waters or provisional waters. In this case, we think that what's going on is sort of a Cold War at sea between China and Japan. There's water cannons going on, and there's people ships lining up on the borders of these areas. And some reports that they're not really squid boats, but they're sort of militias. It's very interesting, just from a standpoint of just the imagery and what it shows in human activity. This is one of the few kinds of measurements where you can actually make a link between human activity on the surface, and from a space measurement. There's a lot of things we can do with moonlight. So one of the things I mentioned earlier is the ability to see snow cover on the surface. And this is looking over the state of Colorado here. It's hard to see, but this is the Colorado-Wyoming border. This is Nebraska over here. But this is the Colorado Front Range where we are. And there happens to be several large areas of snow on the ground in this scene. And they're hard to see. And they're impossible to see, in fact. The lighter things that you see in this image are clouds. These are some cirrus clouds up here and some low clouds here. The snow on the surface is just not seen. But when you look at the day-night band from that same pass, And I'll orient you here. Here's Denver, this big area of city lights here. These areas show up along the Front Range and up in the mountains as well, these bright white areas. And these are the snow fields reflecting the moonlight. I'll go back to the IR again and the day-night band. You can see those areas popping right up because of the strong reflective contrast that the day-night band provides. Um, Something that's nice about having more than one spectral band, like the OLS had just a visible band and an IR band, but VIIRS has the visible band and like 10 or 11 other nighttime near-infrared and thermal IR bands, which allow us to take this scene and even further decouple it in terms of the clouds, high clouds, low clouds, and such. And so what I've done in this next slide is kind of separated the areas. The blues are just the city lights from a stable light space. If you look at those areas, you can see them popping up. The yellows are low liquid clouds. We use other bands to detect liquid phase low clouds. You can see those popping up in yellow. And then the magenta areas are the high clouds, and we use another spectral difference to look for transparent high clouds, in this case cirrus. And you can decouple all three things in this one graphic. So forecasters who, for example, are trying to understand at night where the snowfields are because they're radiatively important, they are highly emissive, and they create very low surface temperatures when you have a clear sky night in a snowfield. This is the kind of thing where you can have a 10-degree difference in your low temperatures over the snow versus over non-snow covered land. So they're looking for this kind of thing, and if you don't have any information about where the snow is, then that's really going to limit how you can draw out where your forecasts are, and you want to customize your forecast for your users. The moonlight also is useful for looking at ocean surface roughness or smoothness. Moon glint is the special case where you have a mirror reflection off the surface, a specular reflection off the surface. And if you have a rough surface versus a smooth surface, that can really affect the nature of what you're looking at in the glint zone. The day-night band has a really high sensitivity to moon glint. We're looking over the Celebes Sea in this example, an infrared imagery. And you can't see anything, but this is really ocean surface here, but you can't see anything about the structure of the surface. And the thermal infrared is just highly emissive, and you just see its brightness temperature. But with the moon glint and using the specular reflection, you can see a lot more information pop up. And what we're seeing here is a pattern on the surface of the water, a pattern of smooth and rough, which is corresponding to these solitary internal waves that are tidally forced. They're called solitons, that you can sometimes see off of continental shelves. And oceanographers are very interested in these measurements because they provide a unique look at this. You can see the solitons with radar as well, but typically the radar that we have from space are very narrow swath, and they don't give a lot of coverage. This is 3,000 kilometers wide, so you can get a good moon glint view whenever the moon is up, if your geometry is right. You can also, I should also mention, you can use moon glint in addition to looking for these sorts of features. You can see oil slicks, other boundaries, even make some estimates of wind speed based on the surface roughness. I'm showing a lot of examples here. It's just kind of a potpourri of all the things that you can do. But this sensor is so new, and people have not worked with it before. It kind of is. It just makes sense to put it all out there, and then you can imagine that any one of these topics you could go into with a great deal of detail, develop algorithms, and do science. But I'm just giving you a sort of an overview in this talk. Low clouds and fog is another thing that people are very interested in. Forecasters in particular, being able to detect. Thermal infrared has a lot of times seeing low clouds, but with the moonlight reflection, you can bring out those borders, those boundaries. You can see the fog in this case working its way up into the Southern California valleys. You couldn't see anything before. And then over here in South America, you see some clouds in the thermal infrared, but there's also a wide deck of low clouds in this scene. Hard to see with the day-night band. It pops up. Had very little, if no, thermal contrast. And you can actually see it below some cirrus clouds above. That's another important capability, being able to look through optically thin clouds. Cirrus in particular are very strongly forward scattering, and they are highly scattering of visible light. And meanwhile, in the thermal infrared, they're very absorbing. They act almost like shields to anything underneath. In these two examples, we'll see how we can peer right through cirrus clouds that are opaque in the thermal, but very transparent in the day-night band's visible frequencies. So on the left, the northern seas, Chukchi Sea, there's a lot of sea ice up in this area. Difficult to detect, especially in the winter. You don't have a lot of sunlight, obviously, and you can't see through the thin cirrus, even because they're thick in the IR. But with the day-night band, you can actually bring those out. I actually reversed my order of animation here, but you can see through the cirrus and see the sea ice below. So you can see all those structures showing up there. In the previous one here on the right, Antarctica, again, looking right through some of the clouds and revealing a lot of the structure of the sea ice offshore. Being able to see through cirrus is also of interest to tropical cyclone monitoring. A lot of times you'll have a situation where the storm is very sheared and you have a low level circulation where the strongest winds are still that's been decoupled from the upper level circulation. And there's all you see in the thermal infrared is the upper level cold cloud tops, and you might think that this is the actual area of where the storm is, the center of the storm. But in fact, when you bring in the moonlight, you see that the center of the swirl is displaced up to the northwest. If you couple those two pieces of information and leave the thermal in the blue and the day-night band moonlight reflection in the yellow, you can see that there's a fix that needs to be done, an adjustment in this case to the center of the storm. The Honolulu Forecast Office was watching this Hurricane Flossie approaching the coast of Hawaii, and through this particular image, they were able to actually adjust their forecast and improve their warning boxes for the storm. We can also do quantitative things with the moonlight when the moon's available. Realizing that the moon's not like the sun, it's not a self-illuminating body, it's reflecting sunlight, and the moon has an elliptical orbit to it, so some full moons are larger than others. You can have a full moon at apogee or at perigee. And then, of course, you have the lunar cycle itself going from waxing to full and to waning phase. So it's a lot more complicated. The spectral properties of the surface are complicated. You need a model to really get at the structure of moonlight. So we've written a model to do this. This is showing the results of that model over that 0.2 to 1.2 micron wavelength. The y-axis just shows the lunar intensity. The different curves are actually the lunar irradiance spectrally resolved for full moons, for gibbous moons, going through the different parts of the lunar cycle there. The spread in the full moon is because of the apogee full moons versus the perigee full moons, some being brighter, some not being as bright. And the red line is the day-night band spectral response function. So once you have this model, which can predict for you on a given night how much moonlight is available, you can take the day-night band response function and convolve it to that particular spectra, and then you'll know for that night how much moonlight's coming down from the top of the atmosphere. So that irradiance, E, is actually factors into a calculation of lunar reflectance. So you take your current measurement of the radiance on that night, and you normalize it by how much light is coming in from your lunar model. The reflectance is invariant. You can have a very bright target, a cloud, for example, produce a strongly variable amount of radiance depending on how much moonlight is coming in. But if you are always able to normalize by the amount of moonlight coming in, then your reflectance deduced from that will not change. You'll have a constant reflection even though the radiance from the moon is changing dramatically as the lunar phase changes. So the reflectance is sort of more of an intrinsic property of the material that you can use for quantitative applications. This is an example of just comparing the day-night the lunar model against actual observations from Meteosat Severi that was looking at the moon. This is just to show that the model is working well over the full course of lunar phase from new moon all the way to full moon, all the way to new moon again. The points overlap pretty well. One of the examples of what we can do with the moonlight, once we have it quantified and have a reflectance, it allows us to fill in gaps. This is an example off the coast of California where we have low-level stratocumulus. These are optical depths. In the morning, they've changed. A lot of times the optical depths will increase over the course of the night, the natural diurnal cycle of these clouds. But we have no retrieval of what's going on in between. Around 1:30 a.m. is when the day-night band comes across. Now with the moonlight reflectance calculated from the lunar model, we can put that into the same retrieval and do this at night and come up with that intermediate step that was missing. We can imagine that we can do this globally as well. It's not just over little locations. It's a polar orbiter. It has global coverage. The daytime view here of cloud optical depth, and now we can do that at night. So the idea is to try to fill in the diurnal cycle of cloud in that way, in a way that we can't do that right now. I just threw this in here because I was working on it yesterday, and it was sort of a big news story. The Pavlov volcano in the Aleutian chain erupted, and this was on the 27th of March. This is a GOES view of that plume of ash coming off of Pavlov, and this is a photo taken from the air of that same plume. On the right here is VIIRS coming across and seeing that same eruption about 9 hours after the start of the eruption. And the ash plume has made its way to the northeast, and it's tracked really quickly because it's in the backside of this mid-latitude storm. And so this is just looking at IR temperatures, really. If you have really, really good eyesight, which mine isn't good enough anymore, there's actually a hot spot here from the caldera itself. But what I wanted to show you was the idea of combining the day-night band, thermal infrared, and ash detection techniques, all from the VIIRS multispectral information into one graphic. And that's what we're seeing here. In this case, the day-night band is providing all the yellow information. This is moonlight reflecting off of the cloud structure, the low cloud structures, and the snow-covered volcanoes along the Aleutian chain here. The blue areas are the cold cloud tops and even parts of the ash plume itself. And the red is what's called a reverse split window difference. This is 12 minus 11 micrometer brightness temperature difference. There's an ash signature in that difference. And we encode that in a sort of a reddish orange color here. And so for a person who's monitoring volcanic ash and where it's going, and realizing that ash can be very hazardous to jet aircraft, or their turbine blades are damaged by ash. The ash can actually melt onto the blades. They can cause stalls. This is something that they're really trying to avoid. So combining the information, in this case from multispectral measurements from VIIRS, can really help. Then we'll get into natural light emissions. Sticking on sort of the volcano topic for the moment, the VIIRS volcano in South America. This was before the volcano erupted. Now, of course, what happens when you have an erupting volcano, you're going to get ash, of course, but you also might get lava, and that lava is going to emit light. That light's detectable by the day-night band, and you can see that light showing up during the eruption. This is a surface photo of when that eruption was occurring. In addition to the light from the magma, you also have sometimes lightning flashes that can happen in the plume, but day-night band's not seeing that. Wildland fires can also be seen easily during the day, but at night, not so much. You can see one of the major fires here with a hot spot and a little bit of a plume in the infrared. The day-night band with the moonlight allows you to see the ash plume itself, lots of structures on the top of the ash plume, and also the lights from the individual fires. This is the rim fire in California from a few years ago, looking in the IR, and then this is looking with the day-night band, and you can see much more detail on the rim of the fire line itself, as well as smoke streaming off to the north. And this is a little movie over several nights showing the massive expansion of the rim fire. Now, the day-night band is useful in this case for seeing, of course, the smoke and the fire, the lights from the fires. It can see light emissions at a level much more sensitive than thermal bands can. So a small fire in thermal bands will not trigger a hot spot, whereas it'll trigger a bright spot in the day-night band right away. And then also being able to see the smoke and the direction of the smoke can be useful for understanding what the fine scale or the microscale circulations are around the fire. A lot of times the fires are so hot that they're creating their own meteorology in the local area, and you can use the smoke as sort of a proxy for what the low-level flow is doing. So firefighters at night, sometimes they'll just, you know, camp and wait for the daylight to fight the fires. And that's unfortunate a lot of the time because fighting fires at night could be easier. They tend to settle down, the humidity in the air increases. So fighting it at night would be preferable, but they just can't characterize the fire very well at night a lot of the time. With the day-night band, there might be some areas to improve that. We looked at lightning a little bit earlier, and one of the examples, this is just a zoom in on what lightning looks like. It looks kind of strange in the day-night band, and that's because of the way the sensor images. It has a 16 detector stack that sweeps across, scanning. As the satellite moves forward, it just whisks across. And if the top of the storm happens to be flashing at the time where the detector stack whisked across, then it'll see it. And it takes about a second and a half for each of these whisks to occur. So what you can have is, the previous scan, nothing was flashing, and then in the current scan, you get a flash, and you see the whole top of the cloud during the period of the flash, and then the next scan, you don't see it anymore. So you get these weird kind of segmented structures. The day-night band wasn't designed for lightning detection. It's just one of the things it can do, and so it's not a staring sensor. But if you do see lightning and a lot of it in a storm as you're going across, then you can say with high confidence that storm is flashing quite a bit. The last thing is the aurora that we can of course see from the day-night band. This is an area over Antarctica. Just right after the satellite was launched, and some great aurora examples were produced. I have two boxes over this particular example. One right over the aurora itself, and then one off to the upper left there that's sort of away from the aurora. And when we zoom in on those two areas and look closer, you can see that the details of the surface, including the sea ice demarcation between ice and open water there, and even some of the fissures and structures of ice a little bit offshore, are well imaged or well detected in this case on the right. And that's because of the auroral light itself reflecting off of the surface and allowing us to see that almost like moonlight would. Versus over here, we do have a boundary that probably looks a lot like this, but we just cannot see it because there's not enough auroral light to illuminate it. So it gives you kind of an idea that, in addition to the moon, there's other ways of looking at Earth at night with natural light sources. And that led us to sort of a discovery, completely unanticipated capability of the day-night band. And that's being able to see light without the moon at all and no aurora as well, all over the world. So right after launch, we were doing instrument checkout and trying to understand the noise characteristics of the satellite. So when you want to look at noise, you want to look at something very dark. So we looked over the middle of the Pacific Ocean there's no lights, and we looked on a moonless night. So any signal we should see should be, noise, right? Well, wrong. What we were actually seeing was something like this. Something looked very much like clouds. So this is a large domain here, the Pacific Ocean, Australia at lower left, and US at upper right. You can see the city lights. But all this area here should have been black if we were talking about no external sources of illumination. And this is also another example over the Atlantic Ocean where the red line demarcates where the moon was up on the left and illuminating these clouds, and there was absolutely no moonlight on the right where the moon had set. So what could be going on here? We don't have moonlight, we don't have aurora. Well, it turns out it's Airglow. The sensor is in a part of the spectrum where we have numerous emissions from different chemical reactions. So there's a lot of people in the room who are, I'm sure, experts in Airglow. But as you know, it occurs globally. It's chemical processes involving, photodissociation of molecules, recombination, and complex reactions in chemistry beyond that. And that's probably as much as I can say about it, not being a atmospheric chemist, but only to say that there's a lot of things going on in the day-night band's response between 500 and 900 nanometers, from molecular oxygen, atomic oxygen, sodium, and excited hydroxyls. And the little figure on the right here, in the red, is the day-night band response function, and this is a spectra of Nightglow, predominantly hydroxyls. These are the areas in the vertical where most of these emissions occur. Molecular oxygen around 95 kilometers, atomic oxygen 90 to 100 kilometers in the green. This red one here is or the deep red one is the excited hydroxyls, and they have a peak around 87 kilometers up. So my limited explanation of what's going on here is the sun is photodissociating, for example, hydrogen and oxygen, and then through this series of chemical processes that produce ozone, and then they relax to these to this excited hydroxyl species, and you have all of these levels that it can de-excite to, and then in that cascading process, you can have photons of light emitted at each of these cascades, and so like 6-3 means go from 6 down to 3. There's a lot of different complex emissions going on here. In the day-night band, again, its response is between about 500 and 900 nanometers. So it's just clipping the tiny part of the hydroxyl emission that's occurring in these transitions here. If the day-night band had been out here somewhere, or even longer wavelengths, that signal would have even been stronger. What you end up getting, if we're just concentrating on hydroxyls for the moment here in the lower mesopause, sort of around 90 kilometer emissions, is this veil of light. You can see that from the space station as it's flying along. Because of the Van Ryn effect, you look from nadir, you look through a shorter optical path compared to if you're looking at the limb. You can actually see that in surface photography. If you look toward the edge of the horizon, that night glow brightens up. For the day-night band, the same thing happens. It doesn't get all the way to the limb, but it gets through a long enough optical path at edge of swath where you do get a brightening at the edge compared to at nadir. So when we look at the night glow imagery, as I call it, because this is a case where we're only seeing signals from night glow, we see lots of clouds, and that's the clouds reflecting the downwelling night glow. And that you can think of that because of the Van Ryn effect, it's almost like a ring of light 360 degrees around the horizon that's illuminating all the clouds. You don't get shadows on clouds, but you do see the clouds on nights when you may not have expected to see them. But in addition to seeing the clouds and the reflected downwelling night glow, we see other things too. And if we look at the IR imagery, we see clouds, of course, but then with the night glow imagery, we see these little structures. It might be harder to see in this one, but you'll definitely see them south of India here. It says IR, and then the night glow imagery. You see these areas show up. I call it sort of middle atmospheric phantoms. But really what it is just the direct emission, upwelling emission of night glow. So what's causing this structure, though? It's actually the perturbation of that veil of light emission by gravity waves passing through or along in it. Now, gravity waves, of course, are perturbations of the atmosphere with restoring forces of gravity and buoyancy, hence gravity waves. But they're launched by lots of different processes, convection, orography, frontal dynamics, a number of different things. We know that they deposit their momentum as they break or are absorbed in the flow, and they're responsible for when they deposit their momentum in the upper atmosphere, these various circulations, the QBO, the Brewer-Dobson circulation, well-known circulations, all a strong function of gravity wave energy deposition and gravity wave flux. When these waves pass through the mesopause layer, that 90 kilometer thereabouts layer of the atmosphere where the night glow is predominantly occurring, it will modulate the temperature and density structure of that layer and change all those chemistry reactions that we were looking at in a way that you actually modulate the brightness of the night glow itself. So the Suomi NPP day-night band is able to see this during nights when there's no moonlight. So that means about about 2 nights after the last quarter lunar phase until 2 nights after the first quarter lunar phase, going through the new moon part of the cycle. At those on those nights at 1:30 a.m. local time, the moon is just not up above the horizon yet. So when Suomi comes across, those are like the prime nights for being able to see the night glow. Here's some examples of the night glow gravity waves. First, an orographic forcing example. We're looking over Nepal area here in Tibet, and you can see in the IR imagery not much. You see the clouds, but in the night glow imagery, you see these linear structures show up, and these are the night glow gravity waves, actually oriented with the terrain in this case, normal to it. Also, thunderstorms can launch a whole spectrum of gravity waves upward into the upper atmosphere. We have a lot of sensors that sense the stratosphere temperature perturbations and can see these waves there, but the day-night band has seen them up around 80 kilometers, so it's a part of the wave spectra that's made it through the stratosphere and the mesosphere unfiltered. This is an example of that. Southern Texas, we have a large area of thunderstorms. They're launching those waves upward, as in the cartoon, and producing this concentric gravity wave pattern. If you can see that sort of a ring, a bullseye kind of shape around the where those storms were. This is actually what they look like from the surface, concentric gravity waves. This is looking from New Mexico out over Texas from these thunderstorms that are producing these rings of gravity waves. And as they pass through the night glow layer, they're perturbing the brightness, as we talked about. Here's another example over Bangladesh, another big thunderstorm, IR imagery of it here. And this is a look at the day-night band. It's kind of harder to see at this scale, but there's another ring pattern going around it, and this is a composite of the two. But a photographer was actually standing here at that circle looking south, and this is what they saw from the surface, and you can see that concentric gravity wave pattern in the sky. Again, the oranges and the greens are different species, different line emissions from hydroxyl, atomic oxygen, and molecular oxygen, and those occur at slightly different levels, so you get different patterns. Hurricanes over the water, we have strong convection. Sometimes it can produce the same kind of effect of the upwelling gravity wave spectra. And this is IR imagery of tropical cyclone Mahasan in the Bay of Bengal. This is the night glow imagery, and you can see some waves there propagating off. You can see a lightning flash. This is another storm near Taiwan in the Philippines, tropical cyclone Kapu. And this is an IR imagery for that. This is the day-night band, and you can now see the waves that are actually coming off of the storm here. You can see these waves superimposed on top. So this is another question of what conspires to produce these waves. It's obviously eye wall convection, but is there something else, information content in here? Why some storms make these waves and some do not? The upper atmosphere and the winds and the temperature structure serve as filters for the waves. A lot of them don't make it up. They break or are absorbed at critical layers. So is there anything about the upper atmosphere and this process that allows the waves to come through that tells us something about is that a good environment for the storm in the troposphere? These are questions that are unanswered at this point, and we're just starting to go down that path of trying to see what the teleconnections possibly are between what we're seeing in the night glow and what we have at the surface. Frontal waves, this is a large storm off the California coast. You can see night glow gravity waves in the flow. They're transverse to the flow in this case. There was actually a jet streak that we think is responsible for that particular one. This is a zoom in over the Pico Islands in the Azores. Again, you see these little night glow gravity waves there coming across the Azores. There was actually a photographer at the surface who was looking off to the northeast, and this is the photo they took. Again, complex banded structures, same orientation as what the day-night band saw, but in this case it's seeing all the different colors. The day-night band is just a single monochromatic band. Upper atmospheric dynamics, undular bores in the upper atmosphere, propagating along the mesopods and adducting region there. You can see those in the day-night band. This is an example over Mexico, IR imagery, and then we see the bore going across here. This is the trailing wave pattern behind the bore. And an example of a volcanic eruption, this one in Chile, the Calbuco eruption. Um, Very powerful, sent a spectrum of waves upward, just like a thunderstorm might, but much stronger. This is looking at the IR imagery for that particular event. You can see that strong, cold ash top. That's what we're seeing here in this photo. But when we look at the day-night band, we see a clearly defined ring pattern around that storm. And this again is the night glow gravity waves up to around 90 kilometers. This is the first satellite view of this kind of phenomena, a night glow gravity wave pattern associated with a volcanic eruption. And then this is Han Lee's model simulation here of gravity waves from the Wacom model. The idea here is that maybe we can begin to collaborate in this area, understanding these model wave patterns are highly, they're based on something, but is it correct or not? It's the real question. The day-night band can help to resolve that question, perhaps. And in other cases, the model can help explain some of the features that we're seeing in the day-night band. So there's a good sort of cross-pollination opportunity there for these kind of measurements, these sort of novel, high-resolution measurements that are very different from the kinds of night glow measurements we've had up to this point, which have been mostly limb-sounding, very coarse horizontal resolution information. So just to wrap up, looking toward the future, what can we do in terms of higher resolution, maybe multispectral, so we can see those different colors and different lighting types, and a geostationary sensor perhaps, so that we can watch things move. Some ways of looking at this sort of ahead of time are photography from the space station. This is Don Pettit in his jury-rigged Mikasa drill bit that moves the platform that his camera is on, so it compensates for the spacecraft motion, and he can stare at a certain spot as he's moving along on the spacecraft and build up enough signal so that his camera can see a nice clean image. So we have all these International Space Station low light photos that we can compare against the day-night band to sort of assess what we could do. You might remember this from the beginning where we looked at OLS, the coarse spatial resolution, going to much higher order of magnitude spatial resolution for the day-night band. But what if you went an order of magnitude further than this and added color to it? Well, here's your International Space Station view, and now you can see that real details come out, including coloration details from different sort of sodium, orange sodium versus mercury green lighting. Looking over Baltimore, again, day-night band versus something from the space station. These aren't perfect matches. I've done my best to try to match them, but they're not perfectly matched. But you can see things like the Key Bridge, in this case, with its bluish xenon lamps. And then looking over the Squid boat areas again near South Korea and Japan. This is day-night band imagery, and this is what the space station would see from that same view. Now notice that we have coloration in South Korea from sodium lights, the bluish lights from the Squid boats, and then greenish lights from the Mercury lights in Japan. And this is something that the color and the high spatial resolution can give you. Finally, VIIRS have a different tonality of color. These are gas flares in southern Iraq seen by the day-night band. Here's the space station view, and here's what they look like from the surface. So it's just an idea, a tease for the kinds of color information, what color information can give you. And finally, if we had geostationary, we could actually watch these gravity waves move instead of just one shot. This is an example from, not from the day-night band, but from a surface-based upward-looking measurement in Hawaii. On the evening that after the big Tohoku earthquake in Japan in 2011, which occurred just a few months before Suomi launched. So unfortunately, we don't have day-night band for this. But what it saw was a train of gravity waves, just like the ones we've seen in the other examples, passing over the Hawaiian archipelago here. And this red line that's drawn on top of that is actually the surface tsunami as it passed over the Hawaiian Islands. So you can see that it's correlated as it goes across there. You can see the wave pattern correlated with the surface tsunami. So now imagine you stepped back and you had a geostationary satellite that was looking over the whole of the Pacific Ocean, and you would have seen this entire structure of the gravity wave pattern moving across in the night glow. and you could correlate that with where the surface tsunami was at that moment. In fact, they say in the paper, John McAuliffe's paper, that it would be nice if they had a geostationary platform just for that purpose. So, we don't have that yet. We just have one measurement from Suomi. And next year we'll have JPSS-1 launch. It'll carry the day-night band as well. It'll be in the same orbital plane as Suomi. It'll be, current plans are to keep them about half an hour apart to 50 minutes apart, somewhere in there. But the upshot is you'll have two views from the day-night band, and for the first time we'll have a poor man's way of inferring that gravity wave motion. So maybe we'll see something. So to conclude, the day-night band has really emerged as an exciting new capability, the most unique part of the JPSS program. Its imagery has been elevated as a result of that to something called key performance parameter status. That means that they can't take it off with incurring billions of dollars in penalties, so they're going to have it on there for JPSS now. And the official VIIRS environmental data records, they exploit the day-night band only for imagery purposes right now. But as we've seen in the talk, there's so many things that it can do that can augment or complement environmental data records that aren't being used right now. So there's a lot of potential there. And then this unanticipated capability to detect Nightglow is really just opening a new frontier of research for the sensor. So with that, I'll conclude, and thanks for your attention.
Thank you.
So with your Nightglow gravity wave detection, is there any spectral resolution on that? Can you distinguish, say, between the green line and the OA infrared?
Yeah, unfortunately, the day-night band's response function is broadband. It's 500 to 900 nanometers, so it's just a single band. It was really designed for moonlight. If it had been designed for Airglow, then they probably would have done something like the IMAP VISI sensor did and picked a band right on the line and then right off the line. Subtract the two and you get the Airglow residual. But no, we can't do that with this band. No.
And the new JPSS is the same.
Same. Mm-hmm. Yeah. Okay.
Can you just download this as a public researcher and any special software?
Yes and kind of yes. You can definitely download it. It's all out there, public domain. To read and work with the data, it just requires a knowledge of a software like IDL, for example, and it's HDF format. The data are already calibrated as radiances, so if you are able to open up an HDF5 file and plot radiances, then yeah, you can work with the data. Yeah.
And did you see anything in the polar region, somewhat polar region? Did you see any like polar mesosphere cloud or not some cloud?
I have not looked closely for PMCs. I want to though. I haven't done that yet.
In principle, you should be able to see that, right?
Yeah, I think so. Especially if they're very optically thin, and just like with a daytime visible sensor, it has a hard time seeing very optically thin clouds. But if you had a low enough solar illumination angle on them, that could brighten them up enough to probably detect them. I have some imagery that looks like it could be polar mesospheric or stratospheric clouds, but I haven't verified it with like Calypso or any other active sensor to validate that. Yeah.
And also, are there any quantitative analysis on the wave spectral characteristics of the spectrum?
Hoping that will be coming soon. The challenge, as you might have been able to glean from some of those examples, is that there's a lot of noise in the Nightglow imagery. You see a lot of cloud reflection, you see a lot of city lights, and so algorithms that can go in and extract just the wave information without having a bunch of false alarms, those are still being developed right now. We're working on a couple of models right now that try to do some high pass filters across the data and then attempt to find the waves through Fourier analysis. But once we work through those algorithmic challenges and actually extract the waves, isolate them, then we can begin to look at those kinds of problems that you mentioned. Still in the works. Oh, I haven't shown anything on that because the day-night band hasn't seen it. The day-night band's response function is a little red-shifted compared to the OLS, and the bioluminescent responses or emissions are in the cyan part of the spectrum. There's these things called Milky Seas, these widespread areas of ocean that are emitting bioluminescent light. And the day-night band hasn't seen one of those, but the OLS did back in 1995. If you Google Milky Seas, you'll probably find some things about it. But it's really what we think of as a bacterial bioluminescence. So it's a steady light emission. It's not like the flashing lights from wave breaking or from ship wakes. Those are created by dinoflagellates. But the bacterial luminescence is almost like glow-in-the-dark silly putty. You hold it up to the light and put it in the dark, and it's just constantly glowing. And that's what the bacteria do. So if you have enough bacteria so that they start to glow, and you have a widespread enough amount of them to fill in many satellite pixels, then you can see them. It's just a very rare phenomenon.
And is the cost of the day-night band instrument, is that a huge cost kind of in addition to the current?
I think that the way they implemented it was more expensive than it had to be. There's actually solutions to doing this kind of measurement that aren't as cost prohibitive, but the way they did it, decided to do it, was a little bit more expensive, and they ran into some developmental issues, and that was part of the reason that NPOS had its cost overruns, I think. It wasn't just the day-night band, it was other things, but yeah, I think that, the idea is to try to get that technology demonstrated, and then, you have an off-the-shelf thing for next time around. It's lower cost, perhaps.
I'm not curious, the solar farm you were showing in the ocean, and how that affected what you were saying was the surface roughness.
Yes.
And the contrast was dramatic.
Yeah. Yeah. Wait.
How can the solar farm produce that much effect on the...
When you get right to the...
It's not a breaking wave.
No, it's not. No, it's not. It's not a breaking wave, but when you get to that, when you have very, very calm water, you could even have a pure, really bright specular reflectance from the moon off of that surface. If you do anything to that water at all, just roughen it a little bit, it will decrease that really strong mirror reflection quite a bit. And then when you juxtapose those two things next to each other, it'll look like a dramatic change in brightness. So yeah, we've seen enough of those. That was a pretty prominent example. We've seen quite a few of those in other places, like the Strait of Gibraltar is another one that always shows them. Monterey Bay is another one.
Thanks, Steve, again.
All right.
Great talk.
Thank you.